Okay, let's look at some more divisibility properties and congruence properties of the Fibonacci sequence. So first we'll come up with some congruence relations for the Fibonacci numbers, and then we'll look at this remarkable divisibility property, that if D is a divisor of n, then the dth Fibonacci number is a divisor of the nth Fibonacci number. We'll see another recurrence that'll give you a formula for the n plus mth Fibonacci number in terms of previous ones. So for instance, with m being 3, it would say the n plus third Fibonacci number is equal to f2, which is 1, so it's the nth, plus 2 times the n plus first. We'll see another remarkable GCD property. Gives us a very easy way of calculating the greatest common divisor of any two Fibonacci numbers. And then finally we'll look at Carmichael's number dealing with prime factors of Fibonacci numbers. So we had this generated matrix A, 0, 1, 1, 1, and we saw that a to the nth power was a matrix full of Fibonacci numbers. So if I take this equality and I just view it mod Fn, then the entries in these two positions become 0, and we get a to the n is congruent to Fn minus 1, Fn plus 1, a diagonal matrix of this type. Now let's use this congruence identity to derive some new facts about the Fibonacci numbers. So since a to the nk is a to the n raised to the kth power, what does that imply? So right here I've got the matrix a to the nk. That's just the formula we saw last time with nk in place of n. And then I'm going to say, well, that is equal to the matrix a to the n raised to the kth power. But the matrix a to the n is this diagonal matrix when we view it mod Fn. So this is this diagonal matrix raised to the kth power, and it's very easy to raise a diagonal matrix to the kth power. We just raise each entry to the kth power, and thus we have a matrix identity. So to say that this is a matrix identity means that this entry on the left has to match with this entry on the right, and that this entry here matches with this one. So what do we get? So matching all of the entries, we see that f nk minus 1 is congruent to f sub n minus 1 to the kth power mod Fn. And then matching the lower entries, the lower right hand corner, we get the second one. And then matching the upper right corner, Fnk, that's congruent to 0. And that's the most interesting one. So what is this third identity right here really telling us? It says that Fn is a divisor of Fnk. So that means, oh, Fnk, this is just a subscript that's an arbitrary multiple of the number n. So another way of phrasing that is the following theorem. If you give me any positive integers d and n, with d a divisor of n, then the dth Fibonacci number is a divisor of the nth Fibonacci number. Now you notice when I stated the theorem, I've let the d serve the role as the n here, and then the n over here is the multiple. So the dth Fibonacci number is a divisor of the nth. Let's take a look at this with an example. So I've written down the sequence of Fibonacci numbers, and let's just let, say, d equal 3. So it says that if 3 is a divisor of n, then the third Fibonacci number, which is 2, is a divisor of Fn. So every third Fibonacci number should be even. Let's check that out. So F3 is 2, F6 is 8, F9 is 34, and so on. You see every third number is even. Next, let D to be 4. So if 4 divides n, then the fourth Fibonacci number, which is 3, should divide Fn. So every fourth Fibonacci number should be a multiple of 3. 3, 1, 2, 3, 4, multiple of 3, multiple of 3, and so on. And you can just keep going like this. So if 5 is a divisor of n, then, oh, this is interesting, the fifth Fibonacci number is just 5. 5 is a divisor of every fifth Fibonacci number, so F10, there's 55, F15, 610, and so on. So that's the idea of this result. Okay, here's the recurrence that I mentioned we were going to derive. For any positive integers n and m, the n plus mth Fibonacci number equals fm minus 1 times fn plus fm times fn plus 1. So notice this generalizes the defining relationship. When m equals 2, you're getting that fn plus 2 is fn plus fn plus 1. So we generalize that. So, again, one could do an induction proof here, but I think the most elegant proof is just going to use our matrix formulation. So we have a to the n is this matrix of Fibonacci numbers, and then there's a simple identity that a to the mth power times a to the nth power is a to the m plus n power. Okay, now what does that say? So on the left-hand side, you've got fm minus 1, fm, fm, fm plus 1. And then you put that right here, for a to the n. Multiply that out, and we're hoping to get a to the m plus n. So how do you multiply 2 by 2 matrices? I better give myself more space. You would get fm minus 1, fn minus 1, plus fm, fn. And let's see, which one do I have up here? I've got fm minus 1, fn. So let's do first row, second column. First row, second column gives us fm minus 1, fn, plus fm, fn plus 1. Right, first row, second column. So that's the right-hand side in the theorem. And on the other hand, if I just look at a to the m plus n power, which this is going to equal, you'll have entries here, and I'm only interested in the entry in the upper right position. So I'm just going to equate this entry with the entry up here, and plugging it into our formula, we get exactly f sub n plus m. So this entry up here is f n plus m. QED. So it's really simple once you have the right point of view for viewing this. Okay, I want to use this identity to calculate greatest common factors of Fibonacci numbers. So let's start with calculating the GCD of f sub n plus m and f sub m. close that. So take the formula. Like this. And now I'll use the subtraction invariance property of GCDs. So I'm going to subtract Fn plus 1 times this entry and eliminate the entry right before it. Right, this is a multiple of that number, so I can subtract off that appropriate multiple just to eliminate it. And then I use the property we saw that consecutive Fibonacci numbers, these two, what's their GCD? They're relatively prime. So these two numbers share no common factor, therefore this is equal to Fn Fm. All right, next let's calculate the GCD of f sub n minus m and f sub m. And I just want to derive it from star, so I'll rewrite star by saying it's the GCD of Fn and Fm equals the GCD of Fn plus m in Fm. And then just substitute in, let's put n minus m in for n, and what do we get? So that would say f n minus m comma fm is fn minus m plus m, which is fn fm. So you get the same thing whether we are adding or subtracting. You get the two numbers fn and fm. So let's continue with that. So we just saw that for any positive numbers n greater than m, the GCD of fn with fm, I can subtract m from n and it'll be invariant. And so by induction, I'll subtract this index from that one again, and I get the same thing. And so in general, for any positive integer q, I can subtract this index from this one q times, and I get the GCD of f sub n minus qm, comma, f sub m. Well, this is beginning to look like a Euclidean algorithm process. So what happens when we apply the Euclidean algorithm to n and m? So we're taking n to be the big number, so n is, say, q1 m plus r1, and you're calculating the GCD of these two numbers, and so we would subtract it off, and you now have r1m, and then m is the bigger one, so you say m is q2 times r1 plus an r2, and then you have an r1 r2 for that GCD. And now what's going on with the Fibonacci numbers? So we're starting with the calculation of these two, and after subtracting off q1m, we are left now with f sub r1 m as the two subscripts, and then on the next go around we keep the r1 and we subtract off a multiple of this from the m, and that gives us an fr2. And so as we're doing the Euclidean algorithm over here, we keep going until we eventually get down to some r value with a 0, maybe it's on the nth turn, and over here you'll get down to f sub r0, which equals fr. So what is this r value you end up with, the nth term? What is this number right here? That is the GCD of the two numbers we are starting with. So you're ending up with the Fibonacci number whose subscript is the GCD of the two numbers you're starting with. A startling property. So let's restate this as a theorem. For any positive integers, m and n, if you want to calculate the GCD of fm and fn, then by the Euclidean algorithm, it's just the Fibonacci number whose subscript is the GCD of m and n. Let's look at an example. So suppose I want to find the GCD of 21 and 144. There's a couple Fibonacci numbers. Well, 21 is the 8th Fibonacci number, and 144 is the 12th Fibonacci number. And so the theorem says all I need to do is look at the GCD of 8 and 12 and just pick out that Fibonacci number. Well, the greatest common factor of 8 and 12 is 4, and the 4th Fibonacci number is 3. So very quickly, without even knowing what the nth Fibonacci number is, we can calculate the GCD of these big Fibonacci numbers. Here's a special case of interest. What would happen if n is a prime and m is a number less than p? So you're looking at fm, fp. Well, you have to say this is equal to f sub GCD of m and p. And what's that greatest common factor? So p is a prime, m is a number less than p, so the greatest common factor is 1. They're relatively prime, and f1 is just equal to 1. So we've said that every Fibonacci number before the pth Fibonacci number is relatively prime. This fm is relatively prime to fp for all m less than p. Which means, what about the pth Fibonacci number? If you're looking at the prime factorization of fp, it cannot have any prime factor that occurs in any Fibonacci number preceding it. So fp has all new prime factors. And this result actually has a type of generalization called Carmichael's theorem, which says that with the exception of these three Fibonacci numbers, 1, 8, and 144, every Fibonacci number has a prime factor that is not a factor of any smaller Fibonacci number, any preceding Fibonacci number. One thing Carmichael's theorem yields in particular is there's infinitely many primes. Right? We got infinitely many Fibonacci numbers. Each one contains some new prime factor, and so you've got infinitely many primes. I'm not going to prove Carmichael's theorem here other than just to remind you that we've proven it just for the case of a prime, and you can do other special cases. Prime p. But let's take a look at the data. So here are the prime factors of the first few Fibonacci numbers, 2, 3, 5, 8, 13, 34, and so on. I give the factorization into products of primes, and then notice each Fibonacci number should have a new prime factor. So 2, 3, 5, 8 is the exception, 13, 17, 11, 89, 144 is the other exception. And so after we are past these two exceptions, we should find new primes for every Fibonacci number.